Hello everyone. In today's lecture, we'll be starting the adaptive control. So here we are going to discuss how we can make the sliding mode adaptive to handle the uncertainties in the system or parameter variations in the control. So before we proceed to the main design concept, first let me introduce with some notes how it is useful for practical applications. So let me write some notes. Adaptive control is used to handle system with uncertainties or parameters that can vary over time. In our previous example, in the previous aircraft problem, adaptive control can be helpful because the aircraft's dynamics changes due to varying aerodynamic conditions, payload, weight, or fuel consumptions. The adaptive control approach adjust the control parameters in real time to ensure stability and desired performance of the entire envelope of flight. So this is a very important concept to handle the uncertainties and parameter variations in the system. And this variation we can include in the control, and that control can handle this unwanted perturbations or uncertainties in the system can be handled. So we'll take the same example what you had before, and we'll see how we can design the adaptive control for that system. So here we'll be using sliding mode. The sliding mode control, what you have done for the aircraft, we'll take that example and we'll proceed. So here, the system dynamics, we are going to consider the system model or dynamics. The same dynamics, the longitudinal motion of the linearized model of the longitudinal motion dynamics, which is theta dot equal to q and q dot equal to a theta theta plus AQQ plus AUU. And let us define this as equation number 1. So here, first, let us design the control U using sliding mode control. So let us find the error E equal to theta minus theta dz. And based on this error variable, let us define the sliding surface, defining the sliding surface as S equal to K plus E dot. And if you take the time derivative, E dot, no time derivative, if you take the E dot here from this expression, so from this we can write E dot equal to we can write sliding surface. So okay, one more step here. So here E dot we can write theta dot minus theta dz dot. So we can write theta dot. So here we are assuming theta dz is a constant. Okay. So for that we can write here. Also, you can write Q, E dot equal to Q. And using this, our sliding surface, hence, sliding surface can be redefined as K plus Q, right? So in place of E dot, we can write Q here. And let us define, this is equation number 2. Now, we will take the time derivative of this surface, differentiating equation 2, we have S dot equal to K E dot plus Q dot. Or we can write KQ plus Q. We can write in place of Q dot, we can write down this equation, this rotational dynamics here. So we can write A theta theta plus AQQ plus AUU. Okay. And let us, so our system has been defining variable S dot dynamics. So here we can define the Lyapunov function using variable S. So defining the Lyapunov function as V equal to half S squared. And if you take the time derivative of V dot equal to, can write S dot or S into, in place of S dot, we can write KQ plus A theta theta plus AQQ plus AUU. And we have to choose U in this equation V dot in such a way that P dot is negative semi-definite. So for that, okay, let me write. Choose U. It is equation number 3, 4. Choose U in equation 4 such that P dot is negative semi-definite. So from this we can write U equal to 1 upon AU into K1S minus KQ minus A theta theta minus A, Q, Q. Okay. So this is, I hope this is clear, this part actually making the system, sorry, the V dot is negative semi-definite, right? This part we have done during the study of Lyapunov function. Now, the most important part is here, how the adaptive control comes into picture. So here, this A theta, AQ, AU, these are basically stability derivatives. But sometimes it is difficult to find this exact values of this. So for that motivation, let me write some note here, why these are very important part. Note. Assume that the plant parameters. So here plant parameters basically K, A theta, AQ, and AU are unknown. We define estimates A theta cap and AQ cap, these are the estimates, and update them using an adaptive law based on Lyapunov function, Lyapunov stability. Okay. For this, we first define the error between them. So we can say these are the actual and these are the estimates. Okay. So we'll find the error between these and we'll take them in the Lyapunov function, and through the Lyapunov stability, we can find the adaptation laws which can be used to design the robust control. So here, we first define the errors between A theta, okay, between them. I'm just writing between them. Okay. So we can write, let E theta is A theta minus A theta cap, and EQ equal to AQ minus AQ cap. Okay. So taking time derivative of these errors. So taking time derivative, we have E theta dot equal to minus A theta cap dot and EQ dot equal to minus AQ cap dot. So here what you are doing is, since these are the stability derivatives, they have the numerical values A theta, AQ. So we can say A theta and AQ are constant. So based on this, we have this minus sign. And so here we can write. So now what you're going to do is, E theta. Okay, what you're going to do is, so these are basically parameter estimation errors. Okay, which is basically E theta and EQ. Okay. So now we'll modify the Lyapunov function. Now, modifying the Lyapunov function and try to analyze these parameter estimation errors. So what we're going to do is we'll modify our Lyapunov function phi equal to half s square plus 1 upon 2 r1 e theta squared plus 1 upon 2 r2 eq square. So here R1, R1 and R2 actually adaptation gains. And it is generally positive. These are the positive values. So now differentiating this equation, okay, these are 5 and equation 6. Differentiating equation 6, we have v dot equal to is s dot plus 1 upon r e theta dot plus 1 up, okay, r1 r2 eq dot. Okay, so we'll go step by step. So from this already we have s dot. So we need to work on these 3 different terms, and we'll go step by step, and finally we'll come up the stability part, how we can make this p dot negative definite. Okay, so already we have s dot as s dot equal to kq plus a theta theta plus aqq plus auu. This is already you have found. This one, this part, equation 3. And here, now, what you're going to do is, in the control, this control 5, we'll replace a theta and aq by the estimated parameter a theta cap and aq cap. So in equation 5, to make the system adaptive, because in control, we'll be using adaptive loss u, and we'll find the adaptation loss for e theta and eq cap. So what we're going to do is we replace the parameters a theta and aq with their respective estimates, which are basically a theta cap and aq cap in control, and the control expression used to be au u equal to minus k1s minus kq a theta cap theta minus aq cap q. This is cap. Okay. Now this u, this part will substitute here in s. So let us define. This is 7. This is 8. And this is 9 equation. Now substituting equation 9 in equation 8, we are having s dot equal to kq plus a theta theta plus aqq, this is aqq minus Q1 is minus KQ minus A theta cap theta minus A cap Q. And from this we can write, okay, this term cancel, and yeah, these only terms cancel. So from this we can write Q1 is plus theta and A theta minus A theta cap plus Q into AQ minus AQ cap. Okay. And from this we can write Q1 is plus, so here already have defined this. This is E theta and this is EQ, right? Already have defined before. So we can write E theta theta plus EQ Q. Sorry. Q. And let us define this equation number 10. Now, so this is this is S dot we found here. So that we'll be using while we'll taking the final expression for V dot. So in equation 7, this part we are done. Now we'll go to the second term. So in second term, so for this we have 1 upon R1 E theta E theta dot equal to, we can write 1 upon R1 E theta E theta dot, we can write also E theta cap dot, right? This you already have found before, yeah, here. And similarly, we can find 1 upon R2 AQ AQ for the second term. Okay, for the third term, we can write this part, third term. So we can write 1 upon R2 EQ dot, we can write R2 EQ minus AQ dot cap dot. This also we have defined here, this part. So now let us define, this is equation 11 and this is 12. Okay. So now what we're going to do is equation 10, 11 and 12 will substitute these terms in equation 7. Okay, in 7. So let's do it. Substituting equation 10, equation 10, 11 and 12 in equation 7 we have V dot, we can write S into minus K1 S plus, okay, E theta EQ Q plus minus 1 upon R1 E theta cap dot minus 1 upon R2 EQ AQ cap dot. And from this we can write minus Q1 is square plus E theta is plus EQ Q is minus 1 upon R1 E theta A theta cap dot minus 1 upon R2 EQ, AQ cap dot. Okay. And from this further we can write Q1 S squared plus E theta. Theta is minus 1 upon R1 E theta cap dot plus EQ QS minus 1 upon R2 AQ cap dot. Yeah, so now we have some simplified form. Now, anyways, this term always positive definite. I mean, the whole term is negative definite. So now we'll manipulate here in such a way that V dot is negative definite, semi-definite. So here to make second and third term vanish, we have the adaptation laws as A theta cap dot, we can design R1 theta S and AQ cap dot equal to R2 QS. So now these are the adaptive laws. So now if you substitute this equation number 13, this is 13 and this is 14. Okay. Now substituting, okay, let me rewrite that. This is 13, 14, and this is 15. Okay. Substituting equations 14 and 15 in equation 13, we have V dot is less than equal to minus K1 S square. Now it is clear. So we have done the stability proof. And in this adaptive laws, this is the adaptive laws for this controller, what you have done before. And now we'll have the MATLAB code. And before that, we need to have some analysis. So here, by the proper choice of K1, K2, okay, let me write here. Not K and K1, okay. Hence, with the proper choice of K, Q1, R1, and R2, the plant can be made stable. So this is how we can stabilize the system, or we can have the desired tracking performance using the adaptive controls, what you have done here. So now we'll go for the MATLAB simulation for this controller, what you have done here. So the values are taken as the given data are theta desired is 5 degree, theta naught 0.3 radian, Q naught 0, A theta minus 0.8, AQ minus 0.3, AU 0.5, K equal to 2.5, K1 equal to 2.5, R1 equal to 0.1, and R2 equal to 0.1. Okay. So these are the given data we have. And now we'll go for the designing control. sorry, we'll see the simulation, MATLAB simulation for this particular controls. So this is the MATLAB code. This is we have initial values, time spent 10 seconds. This is the OD45, and these are the data and control and the error variable, whatever we have designed in the analysis we have given here. And so please cross check line by line what you are doing here in the analysis and what data we are taking in the code. This is the figure, and this is a theta and epsilon, what the different epsilon for the control purpose, and different values of the parameters are given here also. This is the figure plot. And we can see that the adaptive law control is more robust and strong compared to the control we have done. And here, if you notice here, this is the control input. There is no stuttering, nothing is there. And this is a state variable. It is converging to the desired value very fast. So this is how we can design these adaptive controls in MATLAB. So I'm not going to detail in line by line in the code. So try to do it in your MATLAB window and try to simulate whether you are getting this result or not. And if you want to design the same control for other systems or the system you are handling, currently you can test it and you can see the result. And even you can check for the system robustness for the different disturbance signal. Yeah, you can verify your control efficacy, what you are doing. So let's stop it here. We'll continue the another sliding adaptive control techniques in the next lecture. Thank you.